Recording's rolling. It's Friday, January 30th. So here, let's finish this lab from yesterday. I'll help you guys put the graphs together, show you guys what the graphs look like. Okay. And then you guys can turn this in. My plan is to do textbook puzzles too. So let's see what time we got. Okay. So here's a recap from yesterday. Is you guys had these masses hanging on the springs. Now you guys use one spring over and over and over. You were changing out the mass. Okay. And then you would try different things, like if you let it hang down, how far does it stretch to equilibrium? That's like this picture here. Okay? If you just dropped it, how far would it go maximum? That looks like this here. Okay? I'm making the claim that should be pretty close to 2-to-1 ratio, and the papers I've seen so far seem to align with that. If you let it oscillate, how much time does it take? It should match this, which is actually a different way to get K. Right, one way to get K is through Hooke's law, which is basically this right here. Okay? Another way to get K is by timing the oscillation with a stopwatch and doing some algebra here. All right, so you guys did that. All right, I have a model here, and I'll help you guys put the graphs together on the back using this as a model. Okay. So, all right, so we've got all this data. Now, one thing I've been doing is I've been going through grading these days. One thing I'll check is like, hey, is X max pretty close to double X equilibrium? I mean, might not be exact, right, but is it pretty close? And look, 0.4 compared to 0.2 meters. Yeah, actually, that's exactly double. Right. 14 compared to 8. Yeah, that's pretty close. 10 compared to 6, pretty close. 27 compared to 18. Close enough. 24 to 10. Yeah, 21 compared to 10. Ooh, that's almost exactly double. 42, 24. Yeah, so that's pretty much 2-to-1 ratio, just like I was predicting on this page here. Right, this is about double this. Also, the two different ways of getting K are these pretty close to the same, and all the or a lot of tables I've been seeing today, they've been pretty close. So here all the way down, seeing 50, 60, maybe about 70 here. Here I'm seeing in the 40s, like the mid 40s. Okay, all right. So a little bit of a mismatch on this one. Again, each team had a different spring, and maybe some springs are closer to ideal, and some might be worn out a little bit over the years. Right, that might be why there's a little bit of a mismatch between the oscillating way of calculating K and the Hooke's law way of calculating K. Okay? But they're not that far off, right? All right, here's 50, 60, here's mid 40s. That's right. So how about these graphs on the back? So what is X max versus X equilibrium? So X max, this paper goes up to 0.42, or yeah, so let's scale this. So 0.1, 2, 3, 4. So it goes 0. Oh, let's put meters, right? You got to label the unit is so that whoever's reading your graph knows what's going on. Let's go 0.1, 0.2, 0.3, 0.4. Those are meters, of course. So 40 centimeters. All right, X equilibrium. Well, probably about the same thing. I'll put meters, and let's go. Actually, let's do 5, 10, 15, 20, 25. So 0, 0.05, 0.10, 0.15, 0.20, 0.25. These are all meters. Okay. Let's plot those points. And so 0.2, 0.4, 0.2, 0.4, this point, bam, right there. 0.08, 0.14, 0.08, 0.14, bam, right there. At 0.06, 0.10, 6, 10, bam. 0.18, 0.27, 18, 27, sorry about there. 10, 24, 10, 24, bam. 10, 21, stick right there. And 24, 42. Here's 24, 42, stick right there. Yeah. All right. That's pretty good. Because look at this. Line of best fit. Zip. Okay. And the slope of this line should be pretty close to 2-to-1 ratio. Okay, pretty close to 2-to-1 ratio. Like y equals mx, the slope could be 2. Okay. All right, looks like that. How about the one where we did the weight versus the equilibrium stretch position? Okay, so these weights, well, got the mass in grams here. So guys, 1,000 grams, that's like 1 kilogram. And we'll say that weighs about 10 newtons. So we'll call this, here, I'll put the, yeah, just lose. All right, we'll call it 10. All right, what was the biggest? You guys did it was 1,200 grams. Right. So let's scale this up like that. So we'll put weight in newtons. Let's go 0.24681. So 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2. I'll contain the data there. All right, how far did this stretch? Looks like up to about 24 centimeters. Right. Which is the same axis as before, so I can scale that same. 5, 10, 15, 20, 25, 0, 0.05, 10, 15, 0.20, 0.25. These are, of course, in meters. Got that meters. All right, let's get some coordinates. So 10, 0.20, 10. It's like right there. Bam. At that point. 0.08, 5, 0.08. Wait, why did I? Whoops. I'm so sorry, guys. I got the weight wrong by a factor of 10. All right, sorry. Let's scratch that. This would be 2, 4, 6, 8, 10, and 12. Yeah, 12 newtons. I was thinking, right. I had to switch out of kilograms, go to newtons. So times 10 about. This is 4, this is 2. All right, that's better. All right, so 0.08, 5, 0.08, 5. Bam, right there. What else we got? 0.064, 0.064, bam. 0.18, 9, 0.18, 9, so bam. 0.17, 0.17, bam. 0.1, let's see what was 6. 6 right there, bam. Right. And 0.24 with 12 newtons. It's right there, bam. Okay. Oh yeah. Yeah, see, line does fit right there. It's another looks about pretty close to that. It's like, isn't it? All right, now this next one's kind of funny. We've got these weird manipulated axes, 2 pi quantity squared times the mass versus the time period squared. Now, where I kind of got that from is I just took this expression, I rearranged it to put it in a linear form. So that this k shows up as the slope. So I bet we're going to get a straight line here, but let's find out. Right, so 2 pi quantity squared m. Let's look here. Looks like the biggest number is 9 point something. So let's go up to 10. Let's go 2, 4, 6, 8, 10. So you guys know you're starting all your graphs at 0. It's getting 2, 4, 6, 8, 10. And the unit is kilograms. Because 2 pi is a constant and the mass is in kilograms, so it's all kilograms. And the time period, what's the longest time period? Squared, I should say. Squared. It looks like 1 point something. That's the very last one. So we'll go 0.2, 0.4, 0.6, 0.8, 1, and 1.2. So 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2. And these are in square seconds. Like that. Okay. All right, let's get these coordinates. So we're just grab from these. We're doing these as XY coordinates all the way down. Like I said. So 0.92, 7.9, 0.92, 7.9, bam, it's right there. Plus we got 0.48, 3.1, 4831, bam, right there. 0.35, 2.4, 35, 24, bam. 0.79, 71, 7971. Okay. Okay. 0.60, 3.9, 396 right there. 0.54, 39, 0.54, 39 right there. Next. 1.08, 9.5. 9.5. So right there. All right. Yeah, you guys see the overall trend right there? Overall trend? Zip. Looks about like that right there. Pretty close. Yeah, that's good. All right, you guys getting this so far? Yeah. Now, okay, is that okay? Great. Is working for you guys too? All right, it should be. All right, now, this is what I'm claiming the answer should have been. And we've done these three, and they're all linear, and the slope means something too. Right? We got the spring constant from two different points of view. Like I said, it's come up with equations, so this equation could tell you something about that spring. Is that? All right, now this last one is an oscillation one. This was a little different because it doesn't include all the data. I just want you guys to pick one of the oscillating scenarios. Okay. All right, so it also depends how far you pull the spring, because maybe this was here in equilibrium, and you gave it a little 2 centimeter tug, and like started oscillating like this. But it really depends on how far you pulled it as to what exactly this last one's going to look like. I'm going to assume you pulled it 2 centimeters, okay? Which I didn't actually give you guys a space to record that. Okay? But let's put X in centimeters. Let's go up to 2 and down to -2. Right, so it's oscillating around the equilibrium point, up 2 and down 2. Right, so the total height change could be 4 centimeters. You guys it? Now, so you stretch it here, and then you pull it, and you let go. It starts off like, right. Now, I'm just going to pick one of these rows to make that graph. Let's say row 3. Let's see what happens. Okay. So it looks like the time, I'm going to round this to 0.6. You guys see that? 0.59? I'll just call it 0.6. Okay. 0.6 seconds it took to oscillate. So if that's true, this could be time in seconds. This could be 0.6, and then 1.2, and then 1.8, and so on. Right. So it's just bouncing up, down, up. It just keeps oscillating. Or if there's no frictional loss, it'll create a nice cosine looking curve. Okay. Guys, what do you guys think that cosine curve would look like? Yeah, and every time period it completely oscillates. So if there's one time period, can you guys imagine what the rest of that's going to look like? Yeah. Goes like this. It's like this. Right. If there's a little frictional loss, then the amplitude is going to get smaller, smaller, smaller. Right. But if there's no frictional loss, then it'll just keep doing that for 10,000 years. Right. There you go. There's all the graphs. And yeah, really nice looking data, really nice looking graphs. And so, right. If you have all the graphs finished, you can turn to the grade tray just before you leave class sometime today, and then I will get those points in the grade book for you guys. If you don't think you have everything completed, then you can turn it in on Monday. All right, let's look at you guys' textbook puzzles. Now, one side is chapter 14, which is waves in general and oscillating things. And chapter 15 on the back is specifically related to sound. So I think maybe I'll save these for the sound one for a different day. All right, let's look at chapter 14, vibrations and waves. And let's just go through and, let's just do them in order, solve as many as we can for the rest of class here. Number 69, a spring stretches by 0.12 meters. When some apple's weighing 3.2 newtons or is suspended from it, what's the spring constant? Oh, hey, that's something you guys did yesterday. You guys did a lot of things yesterday, but that looks exactly like the set you guys did. And I can solve this. You guys are writing these down on paper? Because eventually I'll pick up these puzzles from you guys. If we do some next week, then you can just add to these. But whatever we do in class, that's what eventually I'll grade. Okay. So you guys write your name on your paper. You guys write your name. Okay. This is chapter 14, puzzles. Guys, what formula do you think I can use to solve for spring constant?
The one that we use on our lab.
Yeah, one you used on your lab. Right. It has a name, starts with an H. Whose law? Huh?
Hooke's law.
Hooke's law. Hooke's law. Yeah. Here's a free body diagram. We got the weight pulling down. We got spring force Kx pulling up. Isn't that true? Force spring equals Kx. And here's force gravity equals mg. Like that. All right, so I'm going to say mg minus Kx goes to 0. That's newtons. They told us actually, they didn't give us the mass now, but they gave us the full weight. So this whole mg itself is 3.2 newtons. That's equal to, whoops, because it is okay if I add over kx, so k times x. Okay. And then in place of x, let's put 0.12, that's meters. That takes the place of that x right there. Because I just added kx over. Right, okay, so then k is whatever 3.2 newtons over 0.12 meters is. I'm looking at 26.7 Newton per meter. All right. All right, that's pretty good. It's working out. All right. All right, number 71. How much potential energy is stored in a spring with this spring constant, 27 Newton per meter? Which is almost exactly what we got anyway. So maybe they're talking about the same spring. Stretch 16 centimeters. Ooh, guys, what's the formula for energy stored in a spring? Yeah, 1/2 kx squared. Yeah. Right. Yeah, every textbook organizes information a little bit differently. We talked about this last semester, but yeah, let's do it anyway. So 1/2, they gave a k of 27, that's Newton per meter. And they're saying stretch it. Oh, 16 centimeters. What number should I put in for the x? 0.16? Because that would be meters based on saying. And don't forget to square that. All right, see if you guys come up with what I come up with. Did you guys get about that many joules right there? That many joules? There you go. Oh, and it is joules because it's energy, right? Energy, right. So if you have a spring and you stretch it, took some work to stretch it, and then let it go, pow, you get all the energy back. How much energy? Well, how much right there? Back that in numbers. 73. Oh, a force versus length data for a spring are plotted. And this graph. Right? What's the spring constant? And then part B, how much energy is stored when it's stretched 0.5 meters. Okay. Guys, what property of this graph would tell you spring constant? Force versus length.
The slope?
Yeah, the slope. Yeah. Right, because it's just Hooke's law all over again. Hooke's law. Let's do some Hooke's law here. 73. I'll do well, F equals kx is kind of the guiding equation. Here's your y-axis, here's your x-axis, and the slope represents the spring constant. So k equals slope of graph. I guess f versus x graph. Okay. So changing y, we're changing x. So looks like, what's a coordinate on here? I think this is a coordinate right here. So, okay, 0, 0 is a coordinate very conveniently. So I'm looking at 10 newtons of force. Guys, what stretch length corresponds to 10 newtons of force? Yeah, 0.5 meters. Yeah, that's right. 0.5 meters. So put it all together. What's the spring constant?
2. 5. 5. 20.
Or I think it's that, right? Is that right? 0.5? Yeah. All right. Yesterday, I know everybody had a different spring. They were all a little bit different stiffnesses. Somebody had a spring that was almost exactly that. I looked on the box. I think they were labeled like 20, 30, 40, 50, 60 feet per meter. Well, some of them were. Okay. Yeah. So this is kind of in line with the springs you guys were working with yesterday. You can imagine like how stretchy those were. So we're back up. At 74, how long must it? Oh, whoops, we didn't do part B. Sorry, that was part A. Let's do part B. How much energy is stored in the spring when it's stretched a length of 0.5 meters? Right, now, there's a couple ways you can get it. Is how can you answer part B, the energy, straight off the graph? What property of the graph would answer that? Right. It's on a force versus distance graph.
It's 10, right? 10? Is
Huh?
that newtons? It's 10 newtons, right?
Oh, okay. The point I picked to do the last one, there's 10 newtons right here. And that corresponds to 0.5 meters being stretched. So 0.5 meters, 10 newtons. Okay. Yeah, that's that coordinate. Okay. I guess the energy stored in the spring is the area under the curve. Okay, that's one way to get it. Let's do this two different ways. We'll do this area under the curve, and then we'll do an equation. I'll show you the same thing. So energy is area under force versus distance curve. So I should call it E sub S, spring energy. Okay. So guys, this is an area of a triangle, 1/2 base height. So let's do 1/2, 0.5 meters, and then 10 newtons. Guys, what is that? Is that 2.5? And what's the unit?
Joules.
Joules. Yeah, because we're talking about energy. 2.5 joules. Okay. There's another way you could also have gotten that answer. Okay. Did you guys tell me a few minutes ago energy is 1/2 kx squared? Let's try that version of it. So 1/2. We got a k of 20 newton per meter. 20 newton per meter. Let's say we stretched it 0.5 meters, and that's being squared. Let's see what it is from this point of view. It's the same thing. It's the same thing. So whether you look at graph property or the equation, it's all consistent. Hey, you guys good on 73? Happy birthday. At 74. How long must the pendulum be to have a time period of 2.3 seconds on the moon with a very weak gravity field of 1.6 meters per second squared? So, guys, a little picture here. So, we got this pendulum swinging back and forth on the moon. It says a time period of 2.3 seconds. Got a gravity field of 1.6 meters per second squared. And we have to solve for this length. How long should the pendulum be? So that sounds like this right here. You guys think? Right here? Yeah, you guys did a pendulum lab not too long ago. So time period for a pendulum is 2 pi root L on G. Ooh, we're solving for this L, right? Solve for that L. All right, let's go ahead and plug in numbers first. Right. If you were my AP class, it probably had to solve in terms of variables. So, right. At 2 pi root. Okay, we got to figure out how long is this pendulum, and we know the gravity field is 1.6 meter per second squared. Extend my fraction bar, my root. That looks a little better. Yeah. All right, so you just got to do a series of algebra steps. Next, what's the next algebra step?
Square it.
Sure, let's do that. So 2.3 seconds, gonna square that, equals 2 pi quantity squared. And then the square root goes away. Length over 1.6 meters per second squared. Yeah, that was good. First step. All right, now what?
Divide by 2 pi squared.
Yeah, divide by this 2 pi quantity squared. While I'm at it, can I cross multiply this 1.6 meter per second squared? Okay. So the length, the necessary length of the pendulum must be 2.3 seconds being squared times 1.6 meters per second squared divided by 2 pi quantity squared.
Is that a time? So it's a multiply?
Yeah, times this. Yeah, that's a little multiplier right there. 2.3 squared, 1.6. Probably a good idea to do some little calculator practice. Make sure you're correctly getting all the parentheses where they go and so on. I'm getting this many meters. There's about 21 centimeters. 21 centimeters. There. Let's see, does that check out. Does it make sense? Okay. Well, if I had a string in front of me right now and I attached this little lab light on, it's about 20 centimeters long. It's about right here. Okay. And then it would take less than a second to swing back and forth. That's an Earth gravity. Now, if you go to the moon, wouldn't this be going back and forth a lot slower on the moon? Right. Yeah, I can believe 2.3 seconds for that. Looks about right on the moon. See some footage on the moon. Let's see. I can imagine this. Sounds pretty close. All right. Number 75. We got Sears Tower queued up. And Chicago sways back and forth with a frequency of 0.12 hertz. What's the time period of vibration? So the given you frequency is 0.12 hertz. So what's the time? Guys, what's the relationship between frequency and time period? They are what of each other? Starts with an R. Reciprocal. Ah, I know frequency is 1 over time period. And also time period, therefore, is 1 over frequency. They're just reciprocals. Right? So if you want the time period, should I just go 1 over 0.12? And hertz is 1 over seconds. So take the reciprocal. We'll get seconds out of that. 8.3 seconds. Okay. So if you were up there in the tower, say if you were near the top, right, you saw that Chicago wind blowing, called the Windy City, then it takes about 8 seconds to completely cycle. So maybe about 4 seconds one way and then 4 seconds the other way. Okay. Ooh. Dude, guys, why wouldn't you get seasick up there if you had an office in the top of the tower? Guys, a lot of skyscrapers have big dampeners in the top. Right? There are different ways to design a dampener. Right? So oftentimes it's like some like a pendulum or some big ball, some huge mass. Right? Like for scale, a person might be like this big, right? And they got like some big ball and spring. I don't know what the one Sears Tower looks like exactly. You probably Google it. Right? But a lot of skyscrapers have these in the top. Right? So that when it gets really windy and the building starts to want to sway, right? This has so much inertia, it'll dampen the building sway so it doesn't sway as much, can't feel as much. Yeah, right. What else do I want to say about this one? Oh, yeah, here. Actually, let's do a little auditory demo here. Let me pull up something for you guys. Because I want to drive home this right here, we box it in pink. This relationship is, see, time period, frequency, reciprocals. All right, so listen real close here. Do you guys hear 1 beat per second? Right, so that would be a frequency of what? How many hertz? Yeah, 1 hertz. Yeah. So this frequency would be 1 hertz. And what would the time period between beats be? 1 second. Ah, that can be true, right? 1 over 1 is equal to 1. Is that okay? Okay. Now, listen here. Do you guys hear approximately 2 beats per second? So what's the frequency? 2 hertz. And what's the time period between beats? Yeah, 0.5 seconds. 1 over 2 is 0.5. Oh. Yeah, right? Now, if you're hearing 4 beats per second, what's the frequency? 4 hertz. Yeah. And what's the time period between beats? Yeah, quarter of a second. If that was 8 beats per second, what's the frequency? 8 hertz. And what's the time period between beats? 1/8 of a second. Right, you guys see that relationship? Okay. Here, I'm going to Google Sears Tower damping system. Let's see if I get a picture here. Oh, yeah. Actually, here it is. Okay, so I just Googled Sears Tower damping system. Yeah, this is what they look like in general. So that's probably the one in Sears Tower, I suppose. Tune mass damper. Yeah, oh, that's what they call it. Tune mass damper. Here's Sears Tower. Yeah. Ooh, nice picture. All right, put that in the top of your building. All right, a little bonus right there. Okay, all right, guys, back to this. So you can hear some clear beats, right? That was 8 beats per second. What if I kept turning up the frequency? At some point, do you think your brain would not be able to keep track of the individual beats?
Yeah. Line.
Would it sound like a hum? Like, and would that correspond to a musical note? What do you guys think? Frequency is 440 hertz. Guess what that's defined as? An an A note. That's one of your A's right there. All right. All right. See what we got here. Let's do one more. I think I told you guys about earthquakes a little bit. I'm gonna skip down here to earthquakes. 83 earthquakes. This will be the last one. 83 earthquakes. The velocity of transverse waves is this many kilometers per second, and longitudinal waves is a different speed. Okay. By the way, I think we got the speeds backwards. That's okay. We'll go with it. A seismograph records the arrival of one wave 68 seconds before the other wave. How far away is the earthquake? So we'll say V of the. I'm going to switch them just to so it matches my example from yesterday. Longitudinal transverse. Longitudinal is called 5.1 kilometers per second. Transverse, let's call it 8.9 kilometers per second. And we got a time interval, call it delta t, time gap of 68 seconds. So how far away is the earthquake? Okay. Oh, here guys, could you say distance equals speed times time? Okay. And they're the same distance away, but different speeds and different times. So let's use this as a model. I'll set up a system of equations. So one distance could be 5.1 kilometer per second times, well, if this is the slower one, I'm saying it's going to be probably t plus 68 seconds. And equal distance is equal to the faster speed, kilometers per second, times just plain t, right? Okay, is that okay why I set that up that way? Okay, so we have a system of equations here. System. Okay, let's just solve the system. Yeah, we got just enough time to solve the system right here. Well, guys, if x is equal to x, can I just set those equal to each other?
Yeah.
Okay, so 5.1 t plus, here, I'm going to distribute this 5.1 while I'm at it. Okay, so let me do it. So what's 5.168? Okay, that's like 346.8. This would be kilometers at this point. Okay. Is equal to 8.9 kilometers per second times e. Okay. And then you guys can finish this off with algebra. So subtract this over 346.8 kilometers is equal to what's 8.9 minus 5.1, 3.8 kilometers per second. Okay. And then divide by the coefficient, 346.8 over 3.8. Okay. So I'm getting a time of 91.26 seconds. Right. No, that's the time for the faster wave to show up. That's not what they asked. They asked what's the distance. So all I have to do is plug this in for t and I can get the distance. Okay. There's a few ways to do it, but we got just enough time, so I'll just do it one way. Let's take the faster wave, kilometers per second, multiply by 91.6 seconds. So times 8.9. Okay. So the answer is 812 kilometers, which is, well, we're in Florida, so that would be like several states away. Okay, so long way away is that earthquake. You're really subtle with that. All right. Okay, so let's get past quick. If you finish that lap from yesterday, all the graphs, whatnot, you can turn that into the great tray, get you guys points. And yeah, you guys have a good weekend.